Wait, where are we? Stop share. Let's stop to share. Are you guys seeing the whiteboard?
Yeah.
Right. Oh, cool. Let me put you guys around here. I'm recording this as well. Let me put this around here. We're in a corner that doesn't bother me. Hide this. Okay, so let's start by sharing some definitions about a tree. So anyone wants to jump in? Oops. Just mute yourself and share. What do you know? What's a tree?
It is a, what's the data structure? It is like for storage, I guess. And it's like a bunch of nodes connected by their leaves. And there are binary trees and I forgot, what was the other one? It was binary, and then there were trees that had more than two nodes, like three nodes.
That's correct. We call those n-ary trees. N for just many, and or for an undefined number of them. Okay, let me move this around here. So, and then just condensing what Owen said. So data structure, first and foremost, that's the important part, data structure. And what is a data structure? If you get asked what is a data structure, what would you say?
It is a way data is presented.
Close, that was really close.
Oh.
A way in which data is
Organized?
That's correct, that's better. Is
a way that data is organized efficiently for a computer to use.
Okay, then a way in which data is organized and stored, right? In a computer system, and additionally, as Jonathan said, efficiently for a computer to use. Owen, you said something about what else, or anybody else wants to add another bullet point here?
There's a hierarchy.
I said something. Sorry, yeah.
There's a hierarchy. High. How do you spell high? But I don't know how to spell that.
R. No, H-I-E, and then R.
I-E-R.
A. Like A-R. Yeah.
Hierarchy like this?
Yeah.
Well, thank you very much. I don't know why it's hard for me to remember this calling them certain words. There's a hierarchy. Yeah. Owen, you were gonna say something.
Oh, I was just gonna say that it's a way it's presented, the way the data is organized is there are a bunch of nodes that point to nodes that might be associated with it, but or might not be. So it's like node, leaf, node. That's the way it's presented. And just looking at what you have on the right, you can basically the best way to use a tree is to traverse it to get each of the values of the nodes. You could do that by like depth first search or breadth first search. I think I'm saying that right.
That's correct. Wait, so in here, let's do, actually, let me erase something here. Oh, I could have moved that as well. Made up of connected nodes. What
Is that
else
what
is made of connected nodes?
Linked lists?
Linked lists, that's correct. So trees and linked lists are not that far from each other. It's like you can think of trees as the sibling or the cousin of linked list. Connected nodes, and okay. Anything else? I guess like from here, from hierarchy, I would like to say that they can represent hierarchy.
Hmm.
Or is if in our system we need if in our system, in whatever application we are building, we need something to keep track of a hierarchy, a tree will be good for that. Any other thoughts? Anybody else? How about tell me, maybe Savita, tell me anything, tell me something about these nodes. What do you know about these nodes?
Well, the structure of a tree, it has a root, which is the head node. It has parent nodes, and then anything that is attached to the parent nodes are its children, and
Yeah.
anything that does not have children is a leaf.
That's correct. Those are the components of the tree, right? Let's draw something here, but hold on because I think somebody is waiting in the waiting room. Participants notes. And then breakout rooms. Okay. Cool. Right. So, okay. Let's draw a tree here. This. Move this a little bit. Oh, hold on. Let me move the exercises somewhere. These are the exercises that we're gonna do. Like count all the nodes in a tree, check if all values in a tree are even or odd, check if a value exists within the tree. Like how you can search an array to see if it includes a value. We're gonna learn how to do that in a tree. Let's say we wanted to add all the elements in the tree. We also wanna look at that. But let me move this to another place. I think I'm gonna need to.
Oh, a quick question.
Yeah.
Linked lists are not a type of tree.
Could you say that again?
Linked lists, they're not a type of tree.
That's a good question. They are not a type of tree, but they do, but what makes you think so?
What makes me think they're a type of tree?
Say that again?
Is your question what makes me think they're a type of tree?
Yeah, yeah.
Just the structure of it, the way that it linked list has nodes and you can traverse it similarly to the way you would traverse a tree.
Mm-hmm. Yeah, so you're onto something, and that is graphs. Trees are graphs, linked lists are graphs. That's what they have in common. And that's what you're describing, like the nodes and how they are connected to others. They are, graphs is a, graph encompasses linked lists, trees, unit-directed graphs, and so on. So graphs. Graphs is the unifying concept there. Let me.
Thank you.
Yep. I wish this tool had a few more shortcuts, but anyway. So let's say we have this tree. We have like 1, 2, 3, 4, 5, let's say. We said that these are all our nodes. Savita, you said that the root node is the one at the top. The ones at the bottom, or the ones that do not have children, are the leaves. That's sort of the key for you to know that they're the leaves, because they do not have any children, and so on. Now we can consider this a subtree, because if we could, if we were only looking at this, we could say that that node with 3 is our root node, and we have 2 children. And trees are a recursive data structure that, and what we mean by that is that a tree can be made of other tiny trees, basically like this tree. This tree that we have, the one that I'm gonna circle in yellow, has a subtree, the orange, that's not orange, the purple. It's a subtree. Okay. Now, what are these nodes? How can we represent this circle with a 3 inside, but now in a programming language like JavaScript? How is it that we do that? And how is it that we can represent, let me make this smaller. Also, let me go full screen on this. Yeah. So if we want to have a node, how do we create a node, and what are the properties of a node? Oops. Wait, no thoughts? Did you guys read the content? What is, if you had to answer the question, what is a node made of? What would you say?
It needs a parent and a child.
Okay. Let's also define that here. So that is correct that it could have a parent. And in fact, in the DOM tree, which is a tree, the DOM is a tree. You have, when you do like whatever element, let's say you get an element from the DOM with get element by ID, you actually have a property called parent element. And you can see who is the parent of that element. So it could have a parent. That's correct. What else did you say, Graham?
A child node.
You need to have childs, yeah, or children. Let me move this around a little bit. It's okay. And for this case, the one that we're going to be working on today, we have, what are the children that we have?
The children of the parent node, I mean, not the parent node, the root node of 1. So it would be 3. 3 will be the child of 1, and 4 and 5 will be the leaf nodes of 3.
That's correct. But actually, I think might have made a mistake here where I'm asking a binary tree, but we haven't talked about those yet, even though, yeah, we haven't talked about it. So let's go up here. Oh, actually, yeah, let's move to this. We sort of talked a little bit about this. Let me then move this somewhere around here. What are some use cases that you can think of for trees? We talked about one, but what are others? You said like anything hierarchy. But I guess what are some examples of those? More concrete examples.
You could insert into a tree.
But I mean like, I guess like real world trees usage or example you could think of.
Oh, maybe
I know this is a bit
search engine.
A search engine. A search engine uses something that is close to trees called tries. I've never implemented one myself, so you're not totally wrong on that. Yeah, actually, in fact, you're not wrong at all. But that is sort of like another advanced type of tree.
Okay. It's like, is that built on top of a tree? It used to be called a try. It was called a try.
It's a try. It's technically a tree. It's a special kind of tree. Yeah. I think anything hierarchy, so let's say like if you want to keep track of what's it called, the tree you make with your family tree, right?
Mm-hmm.
Actually, I'm thinking that I'm missing something here. Let me see if I can open that. These game controls are all over the place. Let me see if I can move this here.
Is it a good way to organize, like, say you had a bunch of foods and it was like the different cuisines were like the parent nodes, like Italian food, Jamaican food, Vietnamese food, and then under that had different nodes, which was like, for example, Italian food would be like chicken parm, spaghetti meatballs, stuff like that. If you wanted to access like a child of a parent.
That's correct. That's actually that's a good example, where you have that type of information in that hierarchy that you described, where you can have a cuisine be a root node, and then children node are specific dishes, and then if we were to map out all the cuisines of all the world, we will end up with a tree that's like, maybe we can have something like food in general, and then we have Chinese. Oh, I don't know how to spell Chinese. You said what was the example? Thai?
Thai, Italian, I think Jamaican.
Mm-hmm. And then under Thai you have, you said chicken parm?
No, I said that under Italian, but Thai I think might be like, maybe, I think I had some duck one time.
I think those are too hard for me to pronounce, to write. But this could be, yeah, this can be dishes. Dish one, dish two. That's correct. We can represent this information in a tree. Now, this is a tree where today we're gonna look at binary trees and binary search trees. And I feel kind of weird talking to you down here. We're going to talk about binary trees and binary search trees. And a limitation that comes also at a benefit price is that binary trees can only have two children, basically. So we can see that this tree that we draw here for food, for representing food and storing food information, has more than two children, where we have Chinese, Thai, and Jamaican, 3 children of food, and 2 children for Thai cuisine, for instance. This is called a general purpose tree. Let me put that in here. General purpose. And we can talk about it later on. But today we'll focus on binary trees and binary search trees. Okay, now one other example here that we'll add it once we see it is the use of sorting or keeping information sorted in a binary search tree is like #1 use case for that type of tree. Okay, so we talked about the components of the tree. Now let's talk about the types of the trees. I'm gonna move this. Let's move this here. And I think some people mentioned a few of them. Would you remind me?
Binary search tree and a ternary, or not ternary, n-nary.
Okay.
Or binary tree and n-nary tree.
Binary tree. And n-nary tree. What else? What was that? And within binary trees, I think we have like 2. We have within binary tree, we have, well, actually, let's define a binary tree first. So binary tree is a tree that only has 2 nodes, and that's what binary mean. 2 and 2 nodes. We talked about an n-array tree. That can have n nodes. So this tree that we saw in here, this is an n-array tree. Or we could say this is, what is binary? What's after binary? Tertiary? No, I don't know. I don't know enough math to know that. But this tree is like all have like 3 children. So we could say that this is where n is 3, and n are 3. Okay. Anything else in binary trees?
On the lesson, it says under binary tree, binary search tree, and AVL tree, self-balancing. I guess those are the 2 types of binary trees.
Thank you. I was looking for those. Let me select here.
There's also heaps.
That's correct. So in here we have binary search trees, binary search. This is also known as BST, just for short. You will see that searching the internet. We said an AVL tree. And at first I thought AVL meant auto balancing until I looked it up, and it's not auto balancing. But this is known as a self balancing tree. Self balancing BST. And we're gonna see. Remind me to talk about what a balanced tree means. Another type of tree is a heap, and they fall under the binary tree category. And a heap is just there is a min heap and a max heap. What they do is they keep the max heap keeps the maximum or the highest number as the root. The min heap keeps the minimum or the smallest number as the root. So that the smallest or the biggest number is always the quickest to access. And then yeah, we're not gonna go too deep into heaps. In fact, we don't have any content about them. Just know that they are of the trees family. Okay, cool. I think a general purpose tree falls under an n-ary tree. You could say, well, the DOM we said is a tree. The DOM is an n-ary tree because there is, when you have a div, you can have potentially an infinite number of elements inside of that div, making the div be the parent of many other elements of many other nodes, and so on. So, any thoughts so far on what we have covered? Or questions?
Yeah, like if we get like a tree problem, will they just give us like a problem and say use a tree, and then you have to figure out like which tree would be best for it usually? Or
Say that last part again.
no, I said like if I were to get like a tree problem on an interview, would it just be like a general like here's this data, like we want you to like organize it like hierarchically? I didn't say that right. And
Yeah.
they just want you to use whatever tree, or is it like here's a tree, we want you to traverse it this way or do this way?
Yeah, most of the times you are given the tree and you have to do something with it. Most of the times you have to traverse it using one of the traversals algorithms that we'll see in a few minutes. Yeah. Let me move this out here. We sort of talked about this. This is on the lesson. Oh, also, this is a good example that I forgot to mention about a use case for trees. If you wanted to implement a storybook in your application that has multiple endings, you could say that as a tree where as the user is progressing through the pages, they will get to a page where they can pick, if they have a binary tree, they will be able to pick between going left and right, and that could be like, that could be a decision that the character makes on the story, like do they pull the trigger or do they close the door or whatever it is. This is another example of a use case for a tree that could be interesting. Okay, let's get then into some code. Yeah, the next step will be implementing a simple tree and doing some exercises there. So again, we are going to be dealing with binary trees today only. Thus, binary trees and binary search trees are the most common trees. Like I will say, when people talk about trees, most of the time they're talking about a binary tree. And most of the time they're talking about a binary search tree. If they're talking about any other kinds of tree, not more explicitly, or if they're talking about other kinds of trees, they will be more explicit about, oh, is an ABL tree is a heap, or is an n-ary or general purpose tree. So that's why we're going to focus today on binary trees and binary search trees first. Okay, so let me then make this smaller. Oops. Let me close some of this stuff. Here. Okay, so we talked about this. Okay, so here's what a binary tree implementation is going to look like. As I said here, just like in a linked list, we can have like a linked list class and a node class. The linked list just keeps track of like the head, keeps track of the head, the tail, and maybe the count of how many nodes it has in the linked list has. We could also implement that in here. Well, sorry, let me go back a little bit where I said we can have a linked list and node classes. Let me go there. The linked list here. We have a node class. This is for a linked list, a node class that has a value and a null. And with this, just with the node class, we can have a linked list. If we create the nodes like this here, and we just connect the nodes. This here, we're connecting the nodes manually, which is fine for a simple implementation. And by connecting the nodes, we end up then creating the linked list. We could also have what we call a container class, a linked list class that keeps track of the head and the tail and the length. The same could be said for trees. We could have a tree class that maybe keeps track of the root, keeps track of how many nodes it has, and that will be it. And then we can have a tree node class that will keep track of, the node itself, the tree node itself, with a value, a left, and a right. And just like we can have a linked list by just connecting nodes, we can have a tree by just connecting nodes. So this is an example here where we create A through K nodes, and we're saving them in variables with a lowercase letter, but the value of the node will be the uppercase letter. And then what we can do is we're connecting the nodes manually. We're saying, okay, A dot left will be B node. A dot right will be the G node, and so on. And we do that. If we do that, then we built a tree. This is a very basic, simple implementation of a tree that we just built. And we could visualize this binary tree in this way, where we have the A as the root. We have to the left of A, we have B. To the right, we have G, and that's exactly what we said here. To the left of B, we have C, and to the right of B, we have F. It's exactly the same thing that we said here. And if we draw this tree, this is like a visual representation of it. But is there any questions regarding this code that we have right now on the screen? Okay, I also accept no questions.
I have a question.
Yes.
So if you wanted to see everything in this particular tree, you would just have to put A. You don't have to console log root?
Give me an example of something you would like to do.
So usually when you want to see everything inside a tree, you would probably console log the root.
I see. Yeah, yeah,
This
yeah, yeah.
case, would it just be A instead of the root?
That's correct. In here, A is our root because A is the node at the top and is the first node and is the node that through A, just having A, we can get to all the other nodes. And that's sort of this next exercise. So I'm going to copy this to a REPL. You should too. So open a REPL and copy that code.
Alex, how can you send the link to the code?
Sure. Give me 1 second. Is it here? No. It's shot. I just sent it in the Zoom chat.
Thank you.
So I really liked Joanne's question because that is the perfect segue for the next part. Oh, and I actually think I have some questions here for you, and I want to give you a few minutes to do that. Oh. Okay, let's do in that REPL. Let's do these exercises as well. I'm going to. I'll demonstrate one, and then you can do the others. Let me add this here. Or let's do this. I guess we can do this together. But before that, let me quickly grab my water bottle that I forgot outside. Okay, so I think we talked about what the root of this node is. That is node with value A. Right? How many nodes are in the tree? I didn't count them.
11.
11? Okay, I'm gonna trust you. How many levels would you say this tree has?
4. Do we
4.
include the root?
Does the root count?
Yeah, we'll include the root as one level. So we have 1, 2, 3, 4. And the level is sort of abstract. We're gonna get to see like what if we want to visit the nodes at a level order. So we have 4 levels. Now this is a question. Having only access to the root, let's say we can only have access to the node with value A. How can we console log or how can we get to the node with value D and console log its value? Actually, hold on, before we do that, this was one of the most confusing parts, or not most confusing, but I realized that I had this mental picture that was difficult in me understanding trees, and that was what happened when I console log A, which goes back to Joanne's question. Let's take a look at what happens when I console log A. Console log A is a root node, is the one at the very top. And I run this. Oh, tree node is not defined. Oh, I forgot to copy the class. We need this to be able to define it. Okay. Wait, if you get asked about what is a class in JavaScript, what would you say? Like, what comes to mind? Whatever comes to mind, even if it's not the right answer.
It's a way to it's a way for functions to like inherit different it's on my tongue. I don't know why I'm not getting this. All right, it's like a function that where you can pass it's like a structure, like a special function in JavaScript that lets you pass functions to other parts of like your program or whatever. So you have like vehicle, and it's like vehicle dot like drive, or it's like you have a function in the vehicle class, and you can access it by you doing like vehicle dot drive instead of like making a new function every time with the same that does the same thing. Right.
Yeah, I think you're close. I mean, that's definitely part of it. That's definitely part of it. I would say like a class is a blueprint for objects, basically. So whenever you want to make many objects of the same kind that look exactly the same, they have the same properties, that they have the same methods, like driving in a car, you make a class for that, basically. And anything that you create using that class will inherit those properties, will inherit those methods. So here we created this class because we want many objects that have a value, a left and a right properties. And these are the properties that we need to implement a binary tree. And we don't want to, we could implement this manually. Like if we don't want to use the tree node, we could say something like this. Because again, a class is just a factory for objects, or what I like to say a blueprint for objects. We could say this. Say if this is just an object, we could say value A, and that's it. And maybe at this point left is equal to null, and right is equal to null. And this object is not much different from the object that's created by saying new tree node. yeah, if I had some other properties here, that I don't want to get into, this object wouldn't get them because this object was not created with a class. It was not created with the tree node constructor, and therefore the A node. In fact, this will still work. I'm not gonna try it right now, but this will still work. This is just an object. A class is just a factory, a blueprint for objects that we want to have the same structure, basically. Okay. So let me put that back. I think that's another review we could do at some point on object-oriented programming and object-oriented approaches as well. This is object-oriented, where we define this tree node that has certain properties, and we're just going to use it to create many of them. Also, in the example that I said with that object, like I will need to create one of those manually every time when I want to create an object that represents a tree. In this way, I just call the factory function, or more explicitly, I instantiate the class, and B becomes an instance of tree node. Okay, so going back, we said like, let's console log the root. Let's see what we get. Let me make this a bit bigger. That was probably too small. Is this good or too small still? I need your feedback here.
And just like the comparison between classes and objects gets me a little bit, I don't know, like a class can have methods.
That's correct.
Right, but
inherited.
So it's kind of, I don't know.
Yeah, so the class is better than a plain object, because a class can have methods that are inherited to all the children. Let's say, we can have here something like this. Let's go a little bit into that. Get value, or yeah, let's say multiply value. We have this function here, and what this function should do is return that value times 2. Now, because I added that to the class, and let's do it. Let me comment this out. Comment that there. And right here, I'm going to do, because I did that in the class, I only had to change it in one place. Now HG has a multiply value function. H has a multiply value function. If we do console.log h.multiply value. Oh, well, actually, multiply value is not a good one because we have strings here. Let's say reverse. We can reverse the string. To reverse the string, you can say, let's split it in the empty character and let's reverse it. This, and let's join it back. Let's say that we had something like this. This is just an example for object-oriented, not as much explicitly of trees. Now, every single one of these nodes, because they are created out of the same mold or out of the same blueprint, which is the tree node, gets that function. If I do h that reverse value and we invoke it and we execute, oh, great. Let's put hello here so we can actually see the reversing. Okay, we got the value reversed. And you know, keys. If we do that, we get the value of the k node reversed. But that is because we define here a mold for whatever object we want, and we define what is it that we want on each one of those of each one of those objects made out of that mold, and so on. But if I do that with a tree, with an object, you know, if I go back to the example where we have a value of a left left null, right null, then this is an object that does not have this function. It does not have the reverse value function. If we try to do, let's put something like that, a dot reverse value, we get a type error saying a reverse value is not a function. Right? We get that because a was not made out of the blueprint of tree node or out of that class. Therefore, it did not inherit that function. Oh, the last thing here in this topic is, let's take a look at this. When we say, does anyone remember the instance of operator? We say a instance of. Wait, actually, let's try this. Type of A. Let's take a look at the type of A. Okay, so when we do the type of A, we get object. Let's take a look at type of B. Oh, we get object as well. And that's because when you create an object with a class, that's still an object. It's just an object that's inheriting values and structure from the class, but still an object. But let me see. Actually, I don't remember this. One is actually, I think it's for that instance. Get the name of an object type. Now, I guess it's a bit. Oh, maybe we could use it with a constructor. You can see this example here. You can say my array that constructor, and it might work. Let's take a look at that. So if we do a that constructor, let's just see if it works. Okay, we got function object. Function object. Note that we are keying into the constructor. We are kind of going off path here a little bit. We're keying into the constructor key of A, but A does not have a constructor key. It doesn't have a constructor key explicitly defined here. That constructor key is being inherited from the object class. Every object in JavaScript inherits from the object class. That's like the global object class. But let's see, what I want to see is if be that constructor give us something different. Let's try that. Exactly, we got something different now here, where we're basically saying the constructor that was used to create B is the tree node constructor, or the tree node class. The constructor that was used to create a literal object, was just the object. There is this operator a instance of. We can check if a is an instance of a tree node, which you get false for that. And if we do instance of object, should get true for that. If we say B instance of tree node, should get true for that. Let's try. Get false, true, true. A is an object, is an instance of object. B is an instance of tree node. Okay. So the benefits of having a class is that you can inherit values, inherit functionality, like this function that we have, that all nodes get it automatically. If we do it manually, we don't have, we're not getting that inheritance. Or we're only inheriting from the object class, and that's it. Let me put this back. Let's get back into trees. Let's remove this. We can leave this here, keys. Okay. Oh, one thing here, the value can be anything. It can be a number, it can be a string, it can be another object, it can be a linked list, it could be literally anything. Just like we have here strings with one character, multiple characters. It could be an array, anything. The left and the right, they could be anything potentially, but we want them specifically to be a tree. We want them to be other nodes, to be other tree nodes. And we're doing that here. We say a.left is equal to b, which is a tree node that we created here in line 10. Okay, so now we're going to look at this. When we console log a, what we get. When we console log a, we get a lot of stuff, and this can be confusing. This, I remember being confused by this. But what we're doing is, well, when you do console log is doing is executing a traversal algorithm that, and it does it all the time. For instance, when you console log an array, you see the entire array. When you console log an object, you see the entire object. That is because, but if we think about it internally, console log has to go to every single element in the array and print it to the screen for you to see it one by one. And that's the same when you console log an object. When you console log a tree, it's similar. It will start at A, and you will try to console log all the content of A. And at some point it stops, and it just gives you something here like an object. At some point, console logs sees that it's going too deep, and then it stops console logging, and it just shows you like object, because console log is implemented like, when you're not intended to use console log to console log deeply nested objects. And this is what this is like. So my confusion was, and I want to hear your thoughts, in that from this console log, the visualization that I was making is that, okay, we have a tree node with value A. And now the left of value A is a tree node with value B. So it seems like the node with value B, it looks like it's inside of node with value A, right? And same for the right. This is the right of node with value A. And the right of node with value A is a node with value G. And it seems that again, like, seems like A inside has B and G. And I remember thinking that, well, then that must look something like this. If I can, so we have like, oh, this is not, oh, I'm trying to erase. If we have like, node with value A, and inside of that node, we have a left and a right. And these are the nodes with value, was it B and G? I don't remember. B and G. And so initially my thinking was, well, this looks like Russian dolls where they're one inside of the other. And you know, B has, and yeah. What are the nodes of B? Does anyone remember?
C, F,
C and F.
and
And
then for G, H, and K.
so this was, I remember that this was my first mental picture of a tree. Like I was constantly logging the root and I'm like, this is all like inside. And but this is a valid visualization, but it's much more difficult to reason about than if you look at it from this other visualization that we have here on the right. So this is a better visualization than this one, but just have that in mind that basically what is happening here is console logs A, and then I said when console log is console logging an object, it has to go on every single key and console log the values of those. So that's what console log does. Console logs each key of the first node, and it sees that the left key is another object, so it's going to go into that object and console log each key of that other object, which is B. And then it happens the same, and you can see where it gives up. It gives up like at about 5 levels deep. So because it goes onto B, and it has to console log each key of B, and you see that the left is a tree, and it console log each key of that object, and at some point it just gives up and it doesn't want to go any further down. Like for the left and the right of B, doesn't want to go there. It just shows you this object. Any thoughts on like this? Does this make sense, even though it's not the right way of looking at it? Another, yeah.
And we kept going. It didn't stop in 5 levels. Is there a language that doesn't stop, that shows you everything?
I don't really know, but I know that console log has like, I think a depth of 5, like hard coded or something. I don't remember if you can change it. If we wanted to look at it all, what we could do is do JSON-stringify.
There's a way to do that. Okay, perfect.
But JSON-stringify also gives up at some point, I think.
Oh, and it doesn't give you the type.
It doesn't give me the type because this is specializing. Yeah, this is what it will look like, more formatted a bit. We see the left of A. Oh, I don't know why this is pulling it down. The left of A is B, the left of B is C. But what I wanted to explain with this is how they look like they're inside of it. It looks like C is inside of B and B is inside of A. But what's happening really is, and the reason why this is a better visualization, this one here, is because in memory is more something like that. In memory there's a chunk of memory somewhere, and you have there value 1, and you have value 1, and you have a pointer to left and right, and somewhere else in memory, in memory a tree can look something like this. If we have, yeah, let's do, if we could look at the memory, and we had a grid here that represents our memory. I think there's a way to make more straight lines. Yeah, let me try this. find. If we could, for some reason, look at the memory, and we have something like, imagine this is our memory. We could have the tree will be at random places where we have, I'm just gonna represent here the node, let's say node 1. Oops, I need to change the pen. Node 1, we're gonna represent here with this 1. And we say the left and right, that doesn't really, you know, in memory, there's no, well, actually, maybe there is like left and right side, but I'm gonna say, yeah, I'm gonna do the rights, I'm gonna do purple. So the right, let's say the right node lives in here. And then here we're gonna put the right node was 3. And then I'm gonna do blue for the left. The left could live here. Something like that. And then the right of 3, which I'm gonna do again with purple. Say the right of 3 can live maybe here, 2. And the left of 3, let's say, lives actually, I think, let's actually put it like down here. This is 4. So in memory, this data is stored in random places, and what happens is that they're connected, because if I have access to this node here, if I have access to this node, I can get to any of the other ones, because this node has a pointer to some other place in memory. And this is actually like physical addresses. Like there's a physical address that is being saved on that left and that right. And that is an address to another place in memory that we don't know where it is, and we actually don't care where it is. And if you organize these nodes, you can still see the tree like left and right. But it doesn't really matter as long as we have the conceptual understanding of how it's working. But here is like, I just decided to put the right with the right nodes at random places, purple, and using the purple marker, and the left nodes with yellow marker and in the random places. But you can see that they are all connected. And this could be, this could be a random organization where in memory, your tree actually gets stored. So then that is also why like this visualization is closer. Actually, I'm gonna do this. This visualization is closer to this one than to the other one. Okay. So any questions or thoughts on this so far? Okay, let's move on to the Pre-Traversals, because I see that always takes me a bit longer. Well, actually, I wanted to ask this question. Does anyone know, let's say we have only access to A, so we can only deal with A. How can we console log the node with value J? Oh, actually, we were on this one. I want to console log the value, I want to console log the node with value D, but I only have access to A, to the root. Through the root, can I get to the node of value D? If so, how? What should I type?
Would you go with A dot left, dot left, dot left, dot value?
Oh, that's correct. So This also sort of supports what we were thinking about here, that it looks like nested, and you're keying nested, nested objects. It's just that what we call nested objects in memory is this, really, is an object that has pointing to some other place in memory that's another object, and so on. This is also true for linked list. This is where I got the inspiration from, a graph there. And here we're keying into that, but you can think of it nested, or also just jumping from pointer to another pointer to another pointer until we get to a value. Let's console log just this part first. Let's see it. Cool. We see that we get to the last node D, which has a left of null and a right of null. And if we actually want to console the value explicitly, we just console log the value. And this, what I wanted to demonstrate with this point is that through the root, you can get to all the nodes. And that's also true for linked list. Through the head, you can get to any other node that you are looking for. Okay, really quickly, what is the solution for the second one? For J's. Owen.
It is, sorry, a dot right dot left dot right.
Let's take a look. Cool, we
Yes.
console log that node. Let's console log just the value.
Oh, dot value, yeah, sorry.
Okay, so here we're like going left, going right, and navigating. So this is true to all the nodes. We can get to any single node just through through the root. Okay, we're gonna skip on this one.
I have a question about that.
Yeah.
So which one is it? Would it be like in order or pre-order in this case?
Yeah, so in this case, we're not following anyone in particular. We are manually going in to where we want, and that's exactly what we're gonna go next. Like, okay, what if, this is kind of hard coding, right, left, right value, right? What if I wanted to find if J was inside? I don't know where it is, but what if I want a function that returns true if J is somewhere in the tree? I don't know where it is exactly. Let's say we have a giant tree, or we have a tree that was given to us. We don't know how many nodes it has. That's then what we want to do next. Like, you could think of this as similar to in the way in which we can like key into any index of an array, like by hand. But if we actually have to find an element in the array, we'll need to write a function, a loop to do that for us. And we're actually going to use a loop. We're going to use recursion for that. Okay. Any other questions here? Thank you for that question, Joanne.
No problem.
Okay, so let's go on to let's go on. I think the next thing then should be the tree traversal algorithm. So let's take a look at here. Yeah, like these are some questions. What if we wanted to print all the nodes in a tree? What if we want to search a given value in the tree? And the question is, in what order should we visit the nodes? Because in a linked list and in an array, there is a specific order you follow from the beginning to the end, from index 0 to the array length -1, or in a linked list from the head to the tail. There is one path to go, but in a tree you have multiple paths. So in what order should you visit it? And not only that, in what order, but should you go down first, or you go down vertically first, or to the side horizontally first? And that's what we call depth first search and breadth first search. And we're gonna see them like next. I'm probably gonna have only time for this after. Okay, so if we have these trees, breadth first search will, breadth first search will go to 0 first, then to 1, then to 2, then to 3, then to 4, then to 5, then to 6. So if we, we'll implement an algorithm that will print, if we print these nodes, it will print them in that order, 0, 1, 2, 3, 4, 5, 6. That will be breadth first search. And we need a specific kind of algorithm to do that. And we will use, for that, we use a queue. We'll use an extra data structure to be able to do that. Now, then the other approach is depth first search, where you go down into the tree to the leaves first, and then go back up. Breadth first search, there's 3 kinds. There is in order, there is pre-order, in order, post order, sometimes also known as prefix, infix, suffix, that you might find in the wild. For instance, that approach here, if this is, yeah, according to these arrows, this will be in order traversal. Well, actually, by the arrows, we can't really tell. We'll say a few examples here, but the importance here of the arrows is that it goes down first. We're not going to the sides yet. So breadth first search traversal. Depth first is a bit easier than breadth first, because breadth first can be implemented recursively and in a very few lines of code. Breadth first needs an extra data structure, which is a queue, and it will be a bit harder, but not impossible. Okay, so in order, we have this. This is the same tree we had earlier. And again, so there's 3 algorithms for depth first search. That is in order. That's the first algorithm. Pre-order, the second algorithm, and post order. And they are different in the way, in the sequence in which they visit the nodes, basically. So just like in, again, I said we're going to implement this recursive, right? And just like in all recursive algorithms, we need to have a base case. And the base case is usually a trivial small input for a program. That example is if we don't have any root, if we don't get any root, if, this wouldn't really be considered an empty tree. This is just no root at all, thus return. So I'm gonna copy this code. I'll paste it there. And what I will do is I'll call this in order print on A. Right now it shouldn't do anything. Let me console this. Comment this one out. Oh, this is kind of cool. Let me comment those out. Right now it doesn't do anything. What's going on? Let's see. Oh wow, I forgot how to write JavaScript. Right now we don't have anything happening because what is our root here when we call it with A? A node with what value?
A?
That's correct. Thank you, Alanza. A node with uppercase A, right? And that is not null, it's different, not null. We'll do the rest here. Now this is where we have to like do, there's a concept for it, but I don't remember. I think it's something leaf. not sure if it's a cognitive leap, or I don't think it's cognitive, but it's something else. But basically, these algorithms, the in-order, pre-order, and post-order, you can memorize, and that'll be fine. And the idea is for you to understand them, but memorize them can be enough, and memorizing can help you understand them. Basically, we said that a tree is a recursive data structure, because you can have just like we have this tree, we can have subtrees, and a tree can be composed of an infinite number, potentially an infinite number of subtrees. So actually, let's think about this. Let's think about the smallest possible tree we can have. The smallest possible tree we can have will be a tree. Well, okay. This is the smallest possible tree we can have. Okay. Smallest tree could be a tree with a single value. Let's say 1. Right? What is the second smallest tree you could have? A tree with 1 node. What's the second smallest tree you can have?
2 nodes.
2 nodes. Let's say we have 1. And let's actually just put, wait, this. The 1 node and 2 nodes is not much of a difference, but this is the second smallest tree that we can have. Okay. So if let's think about the smallest tree. So if we want to have the smallest tree and we want to console log the value, what would we do in here? We want to console log the value of a tree that has only 1 node. We can just do console log root that value. Right? And for instance, in this case, when we run, we now see A coming up. And if we have a tree with only 1 value, like let's say in order print, let's say we create a new tree here. New tree node, let's say 6.2. Console log 6.2. Okay, the console log that. But we want to console log the left and the right. So here, let's actually make a let's do n1 equal new node, new tree node, and let's have this 3. And 2, and I have 1, have 2 here. And I'm going to connect them now. N1 dot left is equal to N2, N2, N1 dot right. So N3 is supposed to be N3. So the tree that I drew here is, or the tree that I'm making here is this tree. Actually, it's not exactly this one. Let me erase that. Is a tree that has 3 there, 1 here, and 2 here. That is the tree that we have in our, let me see if this is possible. This is the tree that I created with this. Right, and then we can pass in N1. And we get that, the first value. but we wanted to go on to the left and the right and console log those two. So you could say, okay, we console log that log root that left that value, and then after that console log root that right that value, and we get 3, 1, 2. We get 3 first, 1, and then 2. Okay, and that works for the smallest tree. But what if we have a bigger tree, the one we have here, or the one we have above with the letters? We can't just hard-code the values here. What we can do is, realizing that a tree is just made out of subtrees, is call the function again on those subtrees. And this is where, this is like the leap of faith that we need to have. What I'm going to do is I'm going to say in order print root that left. What I'm saying there is just call in order print on the left subtree or on the left node. And if that node is a tree, then go on and do the same thing all over again. And I'm going to say in order print on the root that left. And then let's take a look at what we get now. I pass in N1. We get actually exactly the same, 3, 1, and 2. Now let's pass A, which is our bigger tree of letters here at the top. Now we got everything A, B, C, D, E, F, G, H, I, J, and K. We actually got it in alphabetical order. I made this tree with that intent, that I will visit it in alphabetical order later on. Now, this is where then questions arise, or this is where you might not even have questions, and the meat of the algorithm is here. This 4 lines, or this function is a tree traversal algorithm, that is in order traversal. Now let's talk about why is it in order? What means in order is that here actually I think there is a good description that we have here. Yeah, in order means this is is this in order? Oh, sorry, this is not in order. This is pre-order. Here, let's go to the pre-order one. The only difference is where you put the console log or where you actually process the node. This is pre-order. Pre-order, we can see it here. I should have called this pre-order print. You sure? Yeah. So what pre-order means is that we print the root node first. That's what we're doing here. We print the root node first. And then we print all nodes on the left subtree. And after we print all the nodes on the left subtree, we print all the nodes on the right subtree. The way in which that's happening is by calling the function again. Because this function, because we said a tree is made out of subtrees or nodes that can be subtrees. We just need to call that function again with the subtree, with the left subtree and the right subtree. And that will console log for the left subtree. It will console log now on the left side the root value, where now the root of that call is the left side of our previous root. And I want us to like visualize this in, I'm gonna draw it. But any questions regarding this that you may have? Can I have like thumbs up if the recursion, if you feel like you understand how the recursion is working on here? I have thumbs up for that. It's okay if it doesn't for anyone.
Yeah, I have a question about this.
Yeah.
How is it? I don't understand how it goes and it comes back. Is that about a call stack? What's it?
That's about the call stack, yeah, and that's what we will see next. No, like this order in which this was printed is important. Let's analyze that here. So you can see that this goes back to what we said here. Look at this description. Print the root, then print all nodes in the left subtree, then all in the right subtree. So let's take a look at here this visualization. We have A at first, and it says, okay, print the current node or the root node, and then print everything on the left subtree. So that means that B must be printed before J or K gets printed. And we do A, then B, because we're going on the left of A first. Then on B, we go on the left of B, which is then C. Then on C, we go to the left of C, which is D, and then we see A, B, C, D. Now from there, the question is, well, how does it go to E after having gone down here?
Yeah, that's my question.
And then the answer is the call stack, and that will be ideal if I could help understand that. Okay, so let's go back here. I'm not sure. I will need this tree.
Does it go back to C before it goes to E?
We got some trees.
Yep. No, Joanne, to your question, no, it doesn't go back to C, or it goes back to the, I'm not sure how to explain it correctly, to the context of C. Like when we're in C, our function will invoke our algorithm or our function again on the left and the right, right? And then the left, because we have the left, we have the function to the call to go to the left first will happen first, and that will finish. And once that finishes, we'll go back to the context of C, and because that hadn't finished, we'll call the one on the right. And I think that will be my goal of seeing if we can visualize that. So I'm gonna copy this. And here, yeah, we're making use of the call stack. If we want to implement a depth first search algorithm, not with recursion, iteratively, we will need to have our own stack to use. So let me then make this full screen. And let's draw this tree like somewhere around here. I think. No. Text.
Okay, I'm gonna go.
See you, Ben. Thank you.
Ready.
Let's see. Can I make this bigger? Okay. So now let me just draw this here really quickly. So we have A, B, G. My G's looks like a 6, F, D, E, H, K, I, I's, I, and J. Let's see if I can make this. Okay, so we have our tree. And actually, I want to copy. You know what I want to copy? I want to copy our algorithm. Okay, so now let's do. I think I think I might have done this already, like when we were in the classroom. I'm gonna have the call stack here, and I'm gonna have like the output here. Okay, and the call stack will do something like this. A stack. Okay. Let me put this somewhere around here. Okay, so we call, I'm just gonna call it fn, but that's our function. Right here, let me call it POP. And I'm gonna call the function, we call the function with the root, which in this case is the node with value A. So I'm gonna represent that node with, you know, this is just a drawing. But imagine that's the A node with the value of A. So this goes into, POP goes into the call stack. And in the call stack is empty. It's pop, and we have it here. Okay, and that's, then our line of code here doesn't run because the root is not null. We have A is not null. Then we console log the root.value. The root.value when the node is A, so we console log A. Okay, and then we say pre-order print root.left. What that happens is, note that the code, the call for pop A has not finished. It has to call this one, pre-order print on the left side. So what that does is adds that call to the call stack where we do pop, and the left side of A is B, so I'm gonna put B there. Okay, and note that now we're on this line. We haven't gone to the second line yet. But now we have another call on the call stack, which we call our function now with B. Now we say, okay, B is equal to null, no. We console log root.value. When our node is B, our root is B, then we console log B. Right? And then we say pre-order print root.left. And when our root is B, what's the left of B in this case?
C.
C, that's correct. So we put, this is our call stack is filling up. Those are not removed yet. We put pop with C. And then pop with C executes, and you know our root now here is C. That's not null. We console log the value of that root that was passed, which is C, console log C. And we're gonna see then how is it that it goes back in a few minutes. We console log C, and then we go on again on this line, console log or pre-order print with the left side of C. Now what that does is adds something else to our call stack, which with the left of C, which is D. Right, and then now this node here is no longer C, is D. That's not null. We console log the value, which is D. And we console log with the value, which is D. And then we call pre-order print on the left of D. What's the left of D?
No, there's no.
No, that's correct. So, but that actually makes it onto the call stack. We call pop for pre-order print with no. Okay, so that this node is no longer D, now it's no. And then root null now, triple equals null, true, return. What that does is it ends up removing, it removes this call from the stack because now our function return in that case. Okay, so that return, what happens is for once we got to null, the function return and the call stack has stuff to that's still doing, right? The previous call was pop for D, right? And on the left side, it returned. Now it goes. Now it's going to go on the right side. What's the right side of D? Is again the null. So we put in pop null. When the root is null, it returns. So then that gets popped off the stack. And I need to use, actually, maybe I can use this eraser. Gosh, that takes longer. So on the left of D, it returned null. On the right of D, it returned null. Now the call for D, pop for D, it finally finished because he went on the left of the, oops. It went on the left of, what am I doing? It went on the left of the, and it went on the right of the, and those now return. Then the function when we called it for pre-order print on D finally finished. There is nothing else. There is no more lines here. Nothing else that needs to execute. So it finally finished. Then once the call for D finally finished, then it gets popped off the stack. And this is where it gets popped off the stack. So it gets removed from the stack. And we go back to C. This is what I meant, that it goes back to the context of C, because the function C has not finished. And we saw that we already printed A, B, C, D when we were going down. And now we came back to the context of C. Now, what all the stuff that I erased already was the execution of the left side of C. It was the execution of D, right? Of the left side of C. But, so that means that for, what that means is that for, I don't know why it does that. Oh, I guess, hold on, there is people in the waiting room. Where is this thing? It's incredible that I've been doing Zoom for so a while now, and still there's stuff that I don't remember. Why the heck does it keep erasing my function? Okay. So we saw that we went down on the left side until we saw D. And then we're back at C. So what that means is that when the node was, we go back to when the node was C here. And we finished with the left of C, which was D. But the C function, the one that's currently here on the stack, has not finished because it has to now go to the right. It now needs to go to the right. And what happens there is we finish with the left, we get to the function, to the line where we call pre-order print on the right of C. What that does is it adds that call to the stack with the right of C, which is E. Then, then now the node, the root is E on that context. That's not null. We console log the value of that root, which is E. We try to console log, we call pre-order print on the left of E. That returns null because we know there's no left. We call pre-order print on the right of E. That returns null. We know that that doesn't have a right. Then it finally finish. When we were here on pop E, we put two other calls in the stack, one at a time, one for the left, one for the right. Those finish, and then this function gets removed from the stack. Now the execution for the node E was finally done, and that finished there. Then we go back to this context on C, and now then we realize that the left finished, now the right finished. The right was the E part. Now the function call for C finally finished. It reached the end. There is no more lines down here. It reached the end. The function returned undefined because it went to the left, it finished on the left. It went to the right, it finished on the right. Once the function returns, whether explicitly or implicitly undefined, then the call gets removed from the call stack, and we go back here. So we finish with C. We go back to what node?
B.
B.
We go back to B. I think I just made a mistake. We go back to B, and then we saw that this changing of tools manually, I wish it had some shortcuts, but doesn't have them perfect. Okay, because I can't remove those. But now, once it goes back to B, we saw that we have already printed everything on the left here, right? So the left finishes there for when we call it on B, and now it's gonna go on to the right. So it goes on, it finishes on the left, it goes on to the right, it adds a call for F, it prints up F, it tries to go on the left of F, that returns null, it tries to go on the right, that returns null, then the call for F finally finish, it gets removed from the stack. I didn't put it to begin with, but F gets removed from the stack. And then finally B finished because it executed everything to the left of B and everything to the right of B. And then at that point, and this is the last thing I will leave you with, at that point, we went back to the context of A, and we wait, where did B? Yeah, B got printed here. We finished on the left of A. Now our algorithm will go on the right of A, and this goes back to being the node with value A, right? And now the left of that, the left of value of node A is done. We printed it. We saw the stack going up and down. Now it's going to go on the right. And on the right, it will be the exact same process. Then pop for G gets added. that gets printed, the left of G gets added, and so on and so forth. Questions or thoughts about this? Was this helpful at all?
Very helpful.
Very, very helpful. I finally understood this.
Cool. I'm glad to hear that. And this is true. Like, I will encourage you to do the same thing for the in-order, pre-order, and post-order. You will realize that the only thing that changes is when elements get added to the stack and when they get console logged. If we put the console log in the middle, it's called in-order. If we put the console log at the bottom, it's called post-order. And if you follow this, if you follow the steps that I was doing here, by looking at the code, adding things to the call stack as the code is executing, you will be able to see that then the printed output, we can see here, it's an alphabetical order. But in order and in post order, it won't be in alphabetical order anymore. It will be in a different order. I think. Something that just occurred to me really quickly is, let's say we have here red pre-order. So pre-order, this one goes first. This one goes first. This one goes second, third, four. This might be confusing actually. 5, 6, 7, 8, 9, 10, 11. This is the order in which they will be visited. In post order, we put that green. Let's put in order actually. In order. In order, the order is 1. Wait, hold on. I'm actually confused. Actually, in order is the left first. The left first. So in order is a bit confusing. In order is this one goes first. Then this one goes second. This one goes third. This one goes fourth. 5, 6. 6, 7, 8. Now these numbers are like, you don't know which one belongs to which one. 8. This is 9. This is 10, and this is 11. This is kind of confusing. But in order, you go all the way to the left first. You see that if we start in this is the one. Then we go to the middle or the parent node. That's why this one is the second. After that, we go on to the right. That's why this one is the third one. And that just repeats for everything. From there, we go to the middle of this subtree, which is 4. And then on the right, which is then just F, and so on. And I don't even want to go on to the post order. I think there is, I was looking for this actual image, but I couldn't find it, about where it shows this one by one. I think that will be a good example actually to have in the repo. I might draw it in and add it there. So I think we're gonna need to do a follow-up on this because we didn't actually get to like use this tree traversal to find a value in the node or something like that. So I want to dedicate the next session for us to keep going in this so that we can see the other depth first. We can see the breadth first traversal, and then we go into like binary search tree. Which is just binary tree with an extra rule on how the values are organized. Any final questions or thoughts on this?
So it doesn't matter if it's pre-order in order, post order, it always starts on the left?
Yeah, that's a good observation. Yeah, it always starts on the left. You can start on the right, but you always start on the left. I think somebody just picked, let's go left to right first. Yeah. You could go on the right, but all of these go on the left first.
Do Japanese programmers put right first or not?
I'm trying to see if I know any Japanese programmers. Not really. Like I don't know. But it might be that this was influenced by the fact that I think this was actually I don't remember who the inventors of this was, but I kind of think that they were American. Here, let's do a quick search. Inventors of binary tree. This guy looks, they kind of look American, their names. I'm not sure if I'm biased. Oh, British, from Britain. And who else? Following. Does it say? Oh, they're, okay, I guess they're not American, but they're English. And English is written left to right. So I'm thinking that maybe that could have influenced why they decided to go from left to right. Yeah. Any other questions or thoughts? Oh, man. I forgot something. And I think some people are already left.